Now let's look at several examples. So the first example, example 1, which is on page 3 of slides 5-2. Okay. This is to ask you to find the point that optimizes the function and show if it is a relative maximum or minimum. So here this function is fxy equals to minus x squared plus 16x plus 18y minus 1.5y squared plus 15. Okay, so let's check the second order first. Step 1, check second order conditions. Check second order conditions. So for second order, we need to first derive the first orders, right? So here, fx is, so this is just intermediary steps, but later on, we're going to invoke those results when we are doing first order conditions, okay? So f partial x is minus 2x plus 16. That's it. F partial y is 18 minus 1.5 by 2y, which is 18 minus 3y. Okay, just to quickly explain. So here we're doing partial derivative. As we're doing partial derivative, everything else, including the other independent variable, is considered as constant. So here, when we are doing partial derivative with respect to x, only the first two terms should be considered because everything else will simply constants added to the first two terms. Then the derivative is minus 2x of the first one, 16 of the second term. And then as we are doing partial derivative with respect to y, okay, the first two terms and the last term are considered constant, and they are simply added to the y term, the terms including y, so we just disregard them. Okay, namely their partial derivative equals to 0, so we can omit them when we're writing the partial derivative with respect to y. So only these two terms should be calculated, and the derivative of 18 by y is 18, and derivative of minus 1.5 by y squared is minus 1.5. We keep it, and the derivative of y squared is 2y. So the result is 18 minus 3y. Okay, then here our goal is to check second order conditions. So we are to find second order derivatives. There are 3 possible combination. One is fxx, f partial on x, and then partial on x. So we're working with f partial on x, then take another derivative with respect to x, which is minus 2. Right, the second term is a constant added to this. We just disregard the first term. Is a linear. The derivative of that is only the m, the slope term, which is minus 2. Similarly, f partial on yy, is the derivative of 18 minus 3y over y, right? So the result is minus 3. And fxy, the derivative of that is fx, then take a partial derivative with respect to y. Everything has nothing to do with y, so the result is 0. Or you can check by looking at fyx. So fy, the first one, tells you should be looking at this f partial on y, that's the first order derivative, and then take another derivative with respect to x. There is no x in those two terms, so the derivative is 0. And this also testifies to the Young's theorem, in which the sequence of derivatives should not change the result of higher order partial derivatives. Okay, so now we have these second order conditions. We need to check them. We need to check them with what? With this. Okay, so if you could recall, f partial x, or the second order derivative of f function, if that is smaller than 0 for univariate case, that is a concave case. In a concave case, it's like a cave, there is a maximum, right? And f partial xx, f partial yy greater than 0, that is a convex case. And also we need the cross term to fit as well. So those are the conditions that we need to check. Okay. So then let's just compare our results with those conditions to figure out what are we doing here when we are later on doing the first order, solving the first order conditions. Okay. So here fxx is smaller than 0, fyy is smaller than 0. Okay, those direct derivative or straight derivative conditions are met for the first row here, for the second order condition, right? So you suspect now we are doing relative maximum, but still don't forget to check the cross terms. Okay, so the cross term is fxx fyy should be greater than fxy squared. And let's check it. fxx fyy, that's minus 2 by minus 3, which equals to 6. And here fxy is 0, and its square is also 0. So 6 is greater than 0. The condition is checked. So here, the conclusion is we are solving for a relative maximum here. What we are doing later on is to maximize this function. Okay, so what are we supposed to do for the next step? That is actually step 2, first order conditions. Okay, first order conditions. Please put some highlights on this S. S means plural, plurality. That means actually we will have more than one first order conditions. So what are the first order conditions? The first order condition are just the partial derivative equal to 0. And is that the only possibility of partial derivative in this case? The answer is no. We have another partial derivative. Then we should also write it down here. Okay, so it's f partial on x equal to 0, f partial on y equal to 0. It is similar to what we did in our previous case in section 1 of this chapter, right? It is only here in this case we have more than one first order derivatives, then we will have more than one first order conditions. And for rigor, we need to solve all of them. Okay, so then we need to actually invoke the previous result. That's why I'm writing things down here, right? And then what you need to do is just to copy down, right? So f partial on x, that's the first one, which is minus 2x plus 16 equal to 0. F partial on y, that is 18 minus 3y equal to 0. So the solution of the first one is move this minus 2x to the other side of the equation. 16 equals to 2x, and here it is 18 equals to 3y, minus 3, move to the other side of the equation and change the sign into positive. So we have x star equal to 8, y star equal to 6. So the conclusion is 8, 6 maximizes the function in question. Which is this one.